Science Setters, welcome to today's Grade 10 Physical Sciences show. Today we have a special revision lesson on electricity and magnetism. We have selected highlights from lessons shown early in the term to help you revise and prepare for your June exams. You can download the notes for today's show from learnextra.co.za/live. Now it's time to get on with today's lesson. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision.
So, grade 10s, what I've got in front of me here are a number of different things. We've got some little paper clips, we've got some copper turnings, we've got a little piece of wood with some plastic, we've got some glass, a piece of bronze, metal here, and some wax, okay, or in a candle. Now I want to ask, what things are magnetic? So let's try the candle. Definitely no attraction or repulsion there. What about the brass? Well, this is something maybe you're thinking about, because you might say, but all metals are magnetic. Are all metals magnetic? Well, let's go across and have a look. Can you see, is there any attraction here? No, there's not, but immediately you can see these paper clips getting attracted to those magnets. Okay, I'm going to pull them off and watch how, even though they're not touching, they are getting attracted and jumping up onto the magnet, overcoming the force of gravity as they are attracted by this magnetic force. What about the copper? The copper turnings? No, there is no magnetic attraction there. What about let's go with the paper clips. Let's take them off because they are strongly attracted. What about this piece of wood? Definitely no magnetic pull there. Let's try that piece. And we've got some glass here. Certainly no magnetic pull. So the question is, why? Why are certain things magnetic? And you can see this paper clip very strongly being attracted to those magnets. I'm going to put that down and head across to the board, and we're going to talk about why. So magnetism is an interaction that allows certain kinds of objects, which are called magnetic objects, to exert forces. And those forces can be forces of attraction or repulsion. Okay? On each other without physically touching. So there doesn't have to be contact between them. You saw those paper clips which were on the ground were suddenly jumping up and being attracted to that magnet. That is because they don't physically have to be touching. They are interacting through a magnetic field that surrounds that magnet. So a magnetic field, what is it? It's a region of space where a magnet or an object made of something that is magnetic will experience a non-contact. Now, by non-contact, remember we said they do not have to touch or be touching. Okay? Magnetic fields surrounding there are regions of space surrounding magnetic objects will be able to exert that non-contact magnetic force. Okay, so it's a whole area, a region of space surrounding it. The question is why? Why are certain objects magnetic? Well, it is because we have little particles that are charged particles that are able to move. And so if you think about it, if you've got a moving charged particle, it will have a magnetic field. But what I want you to think about here is what substances have moving charges. Well, let's zoom in to every object, every amount, any matter, okay? So let's go, all matter is made up of what? All matter is made up of atoms. Those atoms have, and I'm going to have to draw it down here, a positive nucleus surrounded by these electrons that are able to spin around that positively charged nucleus. Okay? So the focus here is that all matter is made up of atoms, and therefore is going to have electrons, which are charged particles. They have a negative charge, which are able to move. Okay? And they're moving very, very quickly. So if we consider an electron has a negative charge and it's in constant motion inside the atom orbiting the nucleus. So that means that every little electron is going to have a magnetic field surrounding it. The question is then, why are some things magnetic and other things aren't? Okay? We saw that little piece of plastic attached to the wood did not have a magnetic attraction to those magnets. Well, why would that be? Here I've got a picture of a plastic ball. And there's the ball. And what you'll notice is that there are arrows in all directions. That is because the electrons that are inside any object, because all objects are made of matter, which have atoms, so therefore have electrons, they are moving, but they have their magnetic fields associated with them. But those magnetic fields point in all directions. So overall, is this thing going to be magnetic? No, because there is no net or total magnetic field for the whole ball. It's got individual little magnetic fields, but they basically overall cancel each other out. They are not all aligned in the same direction. Whereas if we go across to something that is ferromagnetic. Now, this word ferromagnetic is an important word. You need to know it. Okay? Those are materials like iron, cobalt, and nickel. They can be magnetized. What that means is that they have regions called domains, regions of space called domains, where the electrons' magnetic fields line up. They all align together, okay? And so there is a net overall total magnetic field. So have a look at this picture. What we've got in this picture is an iron needle, so like a needle that you could sew with, right? It's iron, and it's got these domains, and I'm just highlighting one of them there, where all those magnetic fields point in the same direction. And those ones at the bottom all point in the same direction, okay? In each domain, the electrons' magnetic fields are pointing in the same direction, causing an overall net magnetic field. Then you also have what we call permanent magnets, which have all their domains lined up. Sorry. Let's move it down. So now that iron needle has been magnetized and all the domains are lined up in the same direction, not haphazardly, but now there's an even stronger overall magnetic field. Notice that that is a zoomed in picture of the little iron needle. Okay. Now I want us to go back to these types of magnetic materials that we called ferromagnetic. Ferro refers to ferros, which refers to iron. Okay. So if you think about the symbol for iron on the periodic table, it is Fe, ferros. Okay, that's where this part of the word comes from. Okay, ferros. And I've got a periodic table here that I want us to look at. There's iron. Sorry, we just need a pen. There's iron right there, Fe. Okay, the other two that I mentioned to you were cobalt and nickel. Where are they on the periodic table? Let's go and have a look. Next to iron, you happen to have cobalt and nickel. So three of them all in a row share this property of being able to be magnetized. Okay? Very important that you can identify them, and it's quite simple because they're all next to each other on the periodic table. Let's head back to our thoughts here and we've got the idea that things are magnetized. Notice that every magnet has a pair of opposite poles. There is a north pole and there is a south pole. Now, it's important to notice that magnetic poles always have a pair. You can't have a north pole without having a south pole. They have to be paired up. By comparison, what we're going to be looking at next week is electrostatics. Okay? And electrostatics refers to electric charges, where we can have a positive or a negative charge all by themselves. Okay? So just watch out for that. Magnetism is very different to electrostatics. Magnetism, you have, when you've got a north pole, you have a matching south pole. Okay? Because think about why. It's coming back to those domains that are all lined up in the same direction. Right? So electric charges, positive and negative, can occur in isolation. You can have one by itself. You can have an overall positive charge by itself. Whereas magnetic poles that would always be paired up. Notice there that like poles, identical poles, would cause a repulsion. So if you had a north pole and another north pole, they will force each other apart. Whereas if you have unlike poles, a north pole and a south pole, they will attract. We are asked to draw these. So draw the magnetic field when unlike poles. Well, unlike would be opposite. My screen is not playing with me. Opposite. So that's going to mean a north pole and a south pole, opposite poles together. Okay? When unlike poles are brought together, predict what forces will be experienced by the magnet. Well, let's predict first, because I often find that a prediction will help you in terms of your drawing. So, what force will be experienced? And our options are, will it be an attraction or will it be a repulsion? Well, we discussed this right at the end of the previous segment. The idea there that a north pole and a south pole would pull together, attract one another. Okay? So this is going to be an attraction. How would it be drawn? I'm going to put a different color on, and let's draw these two magnets. So there's my one magnet and my other magnet. We need to show one as being north and one as being south. So I'm going to show a north, and then I'm going to show a south, right? The idea is that we're always going away from north. So away from north towards south, away from north towards south, okay? And then it will continue. So obviously weaker as you go around, so further apart. Let's just take that last one away. Probably quite strong in the middle, and the arrows are specifically what we are looking for. Okay? So something like that. Question 2. Like poles. Draw the magnetic field when like poles are brought together. So by like poles, what do we mean? We mean the same. So our options here, these could be two north poles or these could be two south poles, but they're the same type of poles and they're brought together. So either you've got a north with another north or a south with another south, but these are like poles. Predict what force will be. So the force is going to be attraction or repulsion. You answer, it has to be repulsion, because these two are the same thing and they're going to force each other away. The diagram that we're going to draw is going to be quite different. Here I'm going to have a north, and so this one's also going to be a north. Then we want to show away from north. And so this curvature is going to be away, and I think, and obviously in both directions. And our arrows, once again, are incredibly important to indicate away. Now, I think it would be helpful for us to visualize what these would be in terms of a memo. And I actually see here, that would be when like poles repel each other. Notice that the arrows are pointing away because that is north and that is another north. They are pointing away. So the field lines we say that they diverge. They are spreading away from one another. On the next page, I happen to have these like ones. Unfortunately, they swapped around, but it's okay, we can go with that. There we have unlike poles attract. So this one is a north to a south. Okay. There I have from north towards south, and you can see the arrows. I'm just drawing them in for extra to indicate to you that they are always from north to south and very tight at the poles there, very close together. Why? Well, because that's where it's going to have the most highest concentration in terms of the magnetic fields. Okay, so the strongest magnetic field indicated by the lines that are very close together.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. We have got such exciting news for you. From July, a new program starts on Mindset just for you. It's called Connections. We'll chat about the issues that affect your life, your school, and your relationships. We'll have fun, take your calls, and have great prizes up for grabs. Connections from the 1st of July, 7:30 in the evening, only on Mindset. For you, by you. Welcome back from the break. I know you can't wait for the term to end and the July holidays to start. And of course, that means winter school. This year, we will be repeating all the Term 2 Learn Extra live shows for you from the 24th till the 28th of June from 9 a.m. in the morning till 7 p.m. at night. So don't miss out. Go to our website www.mindset.co.za/learn/extra/winter school to get all the details and to download the notes for each lesson. But for now, let's get back to today's revision lesson. Over to you.
Let's get straight into some questions. So I have got a question here I have two charged spheres, each hanging from a string, as shown in the picture below. So there they are. Notice they are two positive charges. So immediately, before I even look at the question, I'm noticing they are like charges, and so they will repel. Okay? Because notice this question gives me options. The spheres will. And so we have our list. It's very helpful whenever you come across multiple choice questions to see if you can answer the question before looking at the answers. Write down a few points to yourself as you're working it out. Okay, because those options given to you in the multiple choice question are designed to give you options that are very close together. And if you start to get confused, it becomes much trickier. So I know they're like charges. I know they're going to repel. So the spheres will swing towards one another immediately. I know they're repelling, so therefore will swing away from one another. So immediately I can cross off A is definitely not correct because of this word towards. Swing away, well, that's true. Swing towards, definitely not. That's not true. Or swing away, okay? So my only options are B and D. I've already cancelled out 50-50. I've taken away 2 options. So B, they will swing away from each other due to the attractive electrostatic force between them. Well, is this an attractive force? No, it's a repulsion. Let's look at option D. They will swing away from each other due to the repulsive electrostatic force. That is true. So my option here is D, and that was not true. D was my final answer I would pick. Okay, so do you recognize how you can answer a multiple choice question quite easily if you work through them bit by bit? Let's go through another one. Now, I heard a question, Katlego, remind me, I heard a question about conservation of charge. Now, conservation of charge, am I right?
Yes, there
Someone's
was.
asking on the page. Conservation of charge is very, very important. We mentioned it earlier, the idea that charge is conserved. It can't be, it's only transferred, it's not created or destroyed. So the overall charge is constant. The total sum is constant. Conservation of charge, I've got a few extra bits here, but we mentioned it earlier that the charge is not destroyed. It is only transferred from one object to another. Okay? And so if you were to add up all the charges at the beginning and add up all the charges at the end, you would find that they would be the same. Okay? Conservation of charge. Let's go through 1 or 2 more things. Charge is measured in coulombs. That's a new one for you. Each electron, remember it's electrons that are transferred, has a charge of Q is equal to 1.6 times 10 to the negative 19. That number, and I'm going to actually change my pen color because it is such an important value. Okay, we're going to work with it lots today and lots in the future. Okay, so it's quite a nice one to keep in the back of your mind. The overall charge on an object will be Q is equal to N multiplied by Q on an electron. So this is an idea. What happens if I said to you 56 electrons are transferred from object A onto object B? What is the charge now? The object was neutral. It's now gained an extra 56 electrons. What is its charge going to be? Well, this equation is going to help me to solve that. I'm going to jump down and get some more space because this is such an important question. So I said 56 electrons were transferred. Okay, what is the new charge? Well, I've got one more piece of information that's on my data sheet. I have Q of an electron is equal to 1.6 times 10 to the negative 19 coulombs. Okay, and all I have there is to say, well, 56 is the number multiplied by 1.6, the charge of one of them, times 10 to the negative 19. Okay, and that's going to give me a value. You can go and work that out. I don't have the time to work that out now. Let's go back and make sure, but I thought it would be helpful just to plug in those values so that you know what we're talking about with that equation. Conductors allow charge to move through them easily. So metals are conductors. They allow the flow of charge. Excess charge, this would be as if you've got something that's negative. Those electrons are going to want to be as far away from each other as possible. They are repelling one another. So they will spread evenly over the surface of a spherical object. So if you've got like a metal ball, those charges will try and spread as far apart from each other as possible. Insulators, on the other hand, do not allow charge to move through them easily. So very often what we'll find is we've got like this metal ball on a insulating stand to make sure that the charge stays on the metal sphere and doesn't flow down to the earth. Okay? Then identical conducting spheres in contact share their charge. So if something comes into contact and it's identical, by identical we mean the same size and the same shape. The charge, when they come together, it's like they are one object, and they will move between them and spread out evenly over now that one big object. But when we move them apart again, they're going to have shared that charge equally. And so it's helpful to work with this equation. Q of the object would be the same, would be Q1 plus Q2, the total divided by the two objects when you move them apart. And I'm going to answer a question based on this equation in the next segment. So very, very important. We do lots of calculations. I want you to notice that in this chapter, you are going to come across words like nano and micro. Okay? It's very important that you go back and revise some of those prefixes. Nano is often used in this chapter. Nano stands for times 10 to the negative 9. Okay, that's one of the good ones to learn. The last one that I want to mention to you is polarization. Now, a neutral object, say a little ball of polystyrene, doesn't allow electrons to flow through it. It's an insulator. But it can be attracted. Maybe we can have little polystyrene balls getting attracted to the ruler. Okay? The reason for this is that the electrons are not free to move, but the individual little molecules making up that polystyrene ball do get to align themselves so that the edges are slightly closer. If I have the polystyrene ball with its individual little molecules, the one end does get its protons or its positive side arranged that way. Say if I bring a little negatively charged ruler close to it. And so this is called the concept of polarization, where the individual molecules align up, okay, as close as they can. They can't move, but they do just align themselves to get attracted as much as possible. So I have two positively charged metal balls placed 2 meters apart. Now, I always find it helpful to sketch what we've got. So there are the two metal balls, and we have that they are 2 meters apart. Is the electrostatic force between the objects attractive or repulsive? So the question is attractive or repulsive, question mark. Well, they are both positive, so like charges, okay? And we know like charges will repel. So my answer has to be that it will be a repulsive force, not an attractive force, and that will be my answer. The next part, because this has got 2 parts, if I now move the balls so that they are 1 meter apart, okay, that little 1 meter is important. That is now the distance. So I'm just going to redraw this picture, and instead of 2 meters, this distance is now only 1 meter. What happens to the strength? That's my question of the electrostatic force between them. We said if they're closer together, the force will be a lot stronger. So closer together means a stronger force. Okay. The next question. An uncharged hollow metal sphere is placed on an insulating stand. So by metal, we know immediately that it is a conductor. Let's just take that away. It is a conductor. It is placed on an insulating stand. So this does not allow charge to flow to the base. It's on the insulating stand. A positively charged rod is then brought up to it and touches the hollow metal sphere at P, as shown in the diagram below. So what's going to happen here? We've got a positively charged rod. We've got the metal sphere. What happens? Well, surely, while it's touching, we're going to treat it almost as one big object. So electrons are able to move from the metal sphere onto the charged rod. It is then moved away from the sphere. Where is the excess charge distributed on the sphere after it has been removed? So there is now excess charge on the sphere, and that charge will be, well, the rod now has positives but lots of negatives as well, as those electrons from the sphere were transferred across onto the rod. What is the rod left with? Well, it's going to be left with excess protons left over. There's the insulating sphere. Once again, I've got options. They're asking, where is it, the excess charge distributed? Is it still located at the point P when the rod touched the sphere? No, it's not. It is a metal conductor. So charge is free to move. Okay? It is evenly distributed over the outer surface of the hollow sphere. Well, that's looking like a possible option. Okay? Let's go through the others as well. It is evenly distributed over the outer and inner surfaces. Now, I've got a problem here with the inner surface. Because think of it, this is a sphere. If the charges are on the inside of the sphere, then they're going to be closer together than if they're evenly distributed on the outside. And remember, we said that charge will repel, want to get as far away from each other as possible. So that's not an option. No charge remains on the hollow sphere, definitely not. There is definitely positive charge. So my only option is B, it is evenly distributed over the outer surface of the sphere. There will be some charge towards the inner, but it will be far apart.
Now it's time for a break, so don't go away. We'll be right back. Welcome back, Mindsetters. In case you missed my news, starting in July, we have a new program that is going to get you talking. What's on your mind? What are the issues you deal with? How can we help you? Connections will help you with all that and more, so make sure you catch it. For a fun and youthful look at life, connect with us on Connections. But right now, let's do some more revision.
So let's quickly do a question which says to us, and guys, please get used to writing a list. This is exactly how I do it. So we go, oops, yeah, wrong way around. That's not going to help me. All right, 100 joules of work, so that's 100 joules, is done when 15 coulombs, so that's charge, moves through a light bulb. Calculate the potential difference. That's voltage across the light bulb. Nice and simple. V equals W over Q. So that means I'm going to go 100 divided by 15, which gives me, and I have worked these out already, so we don't need to spend too much time on the calculator. I'm hoping you guys can all do that. 6,67 volts. Remember, decimal places, 2 decimal places, okay? You guys are going, oh, this is grade 9 work. We can do this. Let's calculate the current. So they're asking us for I. If 72 coulombs of charge moves past a point in a circuit in 5 seconds. Now, grade 10s, please, you do not have to get nice numbers. You do not have to necessarily get numbers that give you whole numbers as your answer. So I equals Q over T. So I is what we're looking for. So this is 72 divided by 5, and we get 14,4 amperes, capital A. The next circuit's a little bit more difficult, but now we're going to have to do some calculations, okay? So first thing, let's just map it out. In other words, let's see, before we have a little bit of a meltdown, what the circuit is, and then you guys can think about it, think about what I've told you, and then we'll do it after the break, okay? So first of all, we have our current, which comes through, so A3 gets all the current, gets to this point in the circuit where R2 and R1 are. We can now split it, so I'm going to put it in green. I actually do not know if R2 and R1 are equal at this point. I need another color, so let's change it to, I don't know, oh, I like the red one. Okay, so the next one, I'm hoping it doesn't destroy my diagram completely for you guys. And then they come back together, so my total current comes back out, which means total current goes through R3, and there we are. Okay, so now we go, okay, I know that A3 is 5 amps. From the circuit over here, V1 is 4 volts, which then means for me that V2 will also be 4 volts, because it's in parallel. If A1 is 1 amp and my total is 5, that means this must be 4. A4 takes the whole current, so A4 is going to be 5. And then we go, okay, well, we have 2 sections in series, this parallel section and this section, and this one takes 4 volts, that takes 8 volts, which means my battery is 12 volts. And I'm pretty sure right about now, some of you are going, okay, Tracy, you just lost me. I know. So, I want you to think through this. Hopefully you've downloaded the notes, so you've got them in front of you. You can look at them. You can read through the question. We'll go through exactly what we need, but I think Luni's a good place to take a break so they can just think about and process.
Okay.
Before the break, we sort of mapped out or looked at the circuit, and we went, okay, we filled in some stuff, and now we need to go through the questions, all right? So the first question is, what is the reading on A2? Now, before the break, we actually worked it out, okay? We said, well, it's going to be 4 amps. But now, of course, you need to show me the calculations. You always have to show the calculations. So we're going to go, fine. We're looking at question A. Now we need to write it out. Let's do it in purple. I like the purple. So we're doing question A. We want the reading on A2. There we go. That means we're looking for I2. And my total, which is I1, so we keep the, oh, sorry, it's I3. It's the convention given to us in the circuit. So I3 is my total. So I3 is going to be equal to I2 plus I1. And I3 was 5. I2 is what I'm looking for. I1 was 1. That means I2, equals 4 amps, okay? That could be 2 marks, could be 3 marks, all depends on your examiner for that, okay? So we're sorted. We've now proven that it's 4 amps. We're happy. What is the reading on V2? Well, we went and looked and said, look at that, I've already got it. It's 4 volts. Why did we say it was 4 volts? Because it's in parallel, and it's in parallel with V1. So all we have to do is write it in. So we can say, well, V2 equal to V1, which is equal to 4 volts. Nice and easy. Oh, we're loving this right now. Question C. Now they say, what is the reading on A4? We worked that out as well. Can you see why we do this? Because it actually helps us. So we said A3, A4 equal because they're both in series. So I4, which is equal to I3, equal to 5 amps. We're happy bunnies right now. Now we get to the fun question. All right. Calculate the resistance of R1, R2, and R3. R1, R2, R3. Now look what they've done, grade 10s. This is what makes this question so nice, is because I know the current through R2, I know the voltage for R2. I know the current through R1, I know the voltage of R1. I know the voltage of R3, and I know the current through it. All I have to do is put it into the equation. And this is where the naming or the subscripts becomes really important, okay? So if I'm looking for R1, from our diagram, we say that's V1 divided by I1. So we recognize and we go, well, that means it's 4 divided by 2 ohms. We're happy. When we look for R2, it's going to be V2 divided by I2. And V2 was also 4, but the current through it was 4, so it's 1 amp. Okay? Now we're going to do R3. R3 is V3 divided, and you can use I4 or I3, it doesn't matter because it's the same value. So that means it's 8 divided by 5 which gives me 1, oops, I'm lying to you, 1,6 ohms. Okay.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. We have got such exciting news for you. From July, a new program starts on Mindset just for you. It's called Connections. We'll chat about the issues that affect your life, your school, and your relationships. We'll have fun, take your calls, and have great prizes up for grabs. Connections from the 1st of July, 7:30 in the evening, only on Mindset. For you, by you. Welcome back from the break. I know you can't wait for the term to end and the July holidays to start. And of course, that means winter school. This year, we will be repeating all the Term 2 Learn Extra live shows for you from the 24th till the 28th of June from 9 a.m. in the morning till 7 p.m. at night. So don't miss out. Go to our website www.mindset.co.za/learn/extra/winter school to get all the details and to download the notes for each lesson. But for now, let's get back to today's revision lesson. Over to you.
So the first one says to us, calculate the total resistance when they are connected in series. So what that means is if we draw a quick diagram, I like to draw diagrams, it makes it easier. It means, so this is for part A. We have, there's my 2 ohm resistor, and there's my 3 ohm resistor, and there's my 4 ohm resistor. And they're connected in series. So remember I said to you before the break that if they're connected in series, it means that we just add them all together. So that's actually really nice. So we're going to go, my R total would be my 1 resistor plus my 2nd resistor plus my 3rd resistor. So it's just going to be 2 plus 3 plus 4, which then gives me 9 ohms. Okay? Grade 10s, sorry, I've been called everyone grade 9s today. Grade 10s, if you need to use your calculators, please don't be ashamed of that, okay? I know that for some of us, arithmetic isn't our strong suit. That's fine. It's why you're allowed to use a calculator. I also know that come exam time, you get quite pressured. And when you get pressured, you tend to make silly mistakes, and maybe this adds up to 10 or 6, or you multiply them together for some reason. Please just use your calculator, okay? Let's just make life easier. Part B says we take the same 3 resistors, but now we connect them in parallel, okay? So that means, and how they actually get put in, so whichever order you put your 3 in, it doesn't make a difference. So if you put the 2 at the top, the 3 at the top, whatever, doesn't make a difference because it all gives me the same answer in the long run. So that's what it looks like. Now we get to the fun part because we've got to look at our maths really, really carefully, okay? Now, this one gives me that funny, horrible equation, and I'm just going to do another color so we can see it, which says that 1 over R parallel, I'm using the parallel lines from maths, or you could say R total because it's the only one there. We also use RP, so maybe let me do that to make it a bit easier for you guys. So 1 over R parallel, 1 over R1, 1 over R2, 1 over R3. Okay, fraction, so we go 1 over 2, 1 over 3, 1 over 4, and we go, oh, we don't like this. Hopefully you all know how to do fractions on your calculator. I'm very old school with this, so I go, well, I've got to find the lowest common denominator, which happens to be 12. Okay, so that means I would have to multiply the 2 by 12, so that's, by 6 to give me 12. The 3 gets multiplied by 4, 4 gets multiplied by 3. And we end up with, I just want to pull this down a little bit so I've got more space, 13, ooh, that's terrible, 13 over 12. But we're not done, okay, because this is 1 over R parallel. Now, this is where you make your biggest mistake. We realize that it's 1 over R parallel, but we actually just want R parallel. So we go, okay, that means I've got to turn it upside down, and you guys do this. You go equal to 12 over 13, and then your teacher moans at you and doesn't give you any marks. Because mathematically, can I say that 13 over 12 equals 12 over 13? Of course not. Remember that this is 1 over r parallel 13 over 12. So to get r parallel, I flip the whole thing over. So I've got to write, therefore, r parallel equals 12 over 13, which is actually 0.92. And it's tiny. How do I know that my calculation is correct? Because my total is smaller than 2 ohms. Hint, when you're calculating resistors in parallel, the total resistance in parallel will always, 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 I'm sure you got that, always be smaller than the smallest resistance in the circuit, in the parallel section of the circuit, okay? Without exceptions. That's the thing about putting in resistors in series, in parallel, sorry, is that we can decrease the total resistance. So if I have a 1 ohm resistor and a 100 ohm resistor in parallel, the total between those two will be less than 1. You can even go do the math to double check me. Okay. So, what do we have here? A resistor. Resistor has a resistance of 15 ohms. So R equals 15 ohms. Calculate the current, so that's I, that's my unknown, through the resistor when the potential difference across the resistor is 20. So V equals 20 volts. Okay, so we go fine, let's see. R equals V over I. We start with the equation. Okay, so we get 15, and we're going to have 20 divided by I. Okay, now we're going to, this one's slightly different than the voltage, okay, because now we want to, the 15 and the 20 are going to swap places because of the, because I is at the bottom of a fraction. So I is 20 divided by 15, and this is actually a very typical type of answer, actually. 20 divided by 15. Now, on your calculators, if you look at the screen, what is the calculator giving me as an answer? 4 over 3. Grade 10s, that is not your answer. Please be careful. In maths, depending on the question, that is an acceptable answer. You can leave it as 4 over 10. 4 over 3, sorry. Not in science. Never, ever, ever do you leave an answer as a fraction. Because all that fraction is a simplification of your substitution. It's not what I want. We have to have it. And look at that. Didn't even do what I wanted there. Oh, you're kidding. Okay, so now we get another, and I'm actually going to this happen. Now we go, hang on, wait. Gives me 1 1/3. We don't write it like that either. So what I'm going to do is I'm going to change the mode. Okay, so we're going to go to, on your calculator, for science, you really need to have it in linear mode. Okay, because now watch what happens. If I go 20 divided by 15, it gives me 1.33. That's my answer. So what I need you to do, grade 10s, take your calculators off maths display. Put it into linear mode. Then you will not be tempted to leave an answer as a fraction, because it will not leave an answer as a fraction. Okay, this is so important, grade 10s, because it's going to bite you in the bum later on, all right? So this is 1.33 amperes. I don't put the dot on the top to indicate that it's recurring, even though the 3 is recurring. If this had worked out to, say, 1.666666 recurring, I would round it off to 1.67. Please round it off 2 decimal places. And if this was one that I would say now need to use in a further calculation, which I'm going to show you next week, I would use the rounded off value. Okay, don't store the value into your calculators. I argue with people all the time over this. We have lots of fights in my classroom, especially with the people who are like pure maths, and they go, no, I want to keep the decimals. I know you do, but don't. 2 decimal places, use the rounded off numbers. Okay, now, Looney, do you have any questions, or can I do a quick summary, do you think? Because we don't have a lot of time.
We don't have any questions. You can do a quick summary.
Oh, I'm going to have to do a quick summary. Apparently, I don't think I'm brilliant. So, remember what I said today. Resistance is R. Resistors can be measured in, can be connected in series or parallel. We connect them in series in order to increase the total resistance, which decreases the total current. We'll connect them in parallel to decrease the total resistance, increase the current. Then we looked at Ohm's law, which says to us that the potential difference across the resistor is directly proportional to the current through the resistor, provided the temperature remains constant. And the equation for that was R equals V over I. Okay, remember, for the total resistance of resistors in series, we just simply add them all together. When they're in parallel, we go 1 over parallel, 1 over R plus 1 over R plus 1 over R. We calculated, and then we flip them all over at the end. Okay, now all of that is foundation, because next week we're going to tackle the fun part. I want to encourage you to have some colored pens with you. I'm going to have fun with the highlighters on the board. It's going to be lots of fun. We're going to do circuits, and we're going to hopefully get it done.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to join us for winter school from the 27th till the 30th of June, when we will be repeating all the Learn Extra live shows from Term 2. We'll be back with live shows from the 15th of July for Term 3 lessons.